Okay. Excuse me. Let me hide the meeting controls. So good morning and happy Monday. So this weekend we were in Connecticut for a tournament of sorts that my daughter had, and this morning she woke up sick with flu-like symptoms. So I'm going to be extra cautious, making sure that I don't give you what she has given me. That being said, I hope you stayed warm this weekend. Where we were, it was minus 11, the straight temperature. That was like unbelievable. But nonetheless, happy Monday, and the semester is moving on quickly. This Wednesday will mark 3 weeks of classes. And so this Wednesday, you'll be 3 weeks down and 12 weeks of semester left. Certainly spring break on top of that. And I'm sure you're all looking forward to spring break. Maybe you get to go someplace nice and warm or just get a little restoration and relaxation. But that being said, today we will finish up the balance of where we left off on Friday, and that seemed like such a long time ago. But we'll finish that up concerning joint distributions and variable linkages in particular. And then we'll pick up with new material concerning a more rigorous definition and treatment of a probability. What is a probability with an I? Towards what we're going to call complex events. Okay. But before we begin, the usual, excuse me, and hopefully my voice holds out, the usual administrative bits. The reading has not changed. It concerns, why does that not look right to me? I think I have that wrong. Tuesday. Yeah, it is the 7th. All right. Wow. Just seems like today should be a different day from the 7th. Tuesday should be different. All right. So the reading concerns the APIs and guides for PyPlot, which is the visualization API in Matplotlib in Python. And it's certainly not the only set of sources for this material that I've curated in the course resources section on the course Canvas side. I'm so used to saying Moodle. I have to pause when I say Canvas. Project number 2 is due tomorrow evening at the usual midnight hour. Please make sure that you're paying attention to all of the components you hand in. You're going to be handing in your IPython file, which is your Jupyter notebook, and that is different from doing a file save as for your browser, which is running your Jupyter notebook, right? The two are different things. And so for that, you go to the file system in the location or the path where you started Jupyter Lab, and that's where it places these notebooks. I like to collect these things in a single location so that I can always go to that directory and find my IPython files. Any questions? No questions? No? And so what I really want to instill in you and develop in you is the skill set of algorithmic thinking. That's really, really important, whether you ever plan to be a computer science major, data science major, minor, or not at all, right? It's a really, really important skill set. And when you're working on the projects, it's important to focus on your algorithm first before you jump right into the implementation. And I know it's irresistible to do that because at the end of the day, you want to get it all done, right? I get that. But please take pause and take a step back and consider what it is you want your process, your computation to do, and the data structures on which your computation operates. That's a really important skill set. And so any questions? No questions at all? I know that one person handed it in. If you have it done early, wonderful. Hand it in, do your happy dance. You have up to 20 submissions. I'm not going to look at all 20. I'll only look at the latest one. But if you hand it in, if you make a mistake or you forgot something, it gives you an opportunity to correct that. So please hand it in early. If you have it ready, do your happy dance. I'm about halfway through the grading of project number 1. And so I will push that out and I'll let you know they're posted. I expect you to take a look at Canvas regularly I use extensive feedback or give extensive feedback where necessary in a digital form. And I'm also still learning how to use Canvas to do that because my muscle memory is tuned to Moodle. Okay. Any questions? No? All right. So where we last left off, we talked about a so-called joint probability. And we depicted it in table format. And in this particular visualization, we have on our rows the outcomes of a coin flip, 1 through 6. And for our columns, we have the outcome. Oh, I'm see, die roll, see if you're paying attention. Along the rows, rather, we have the outcomes of a die roll. And along the columns, we have the outcomes of a coin flip. And so variable or random variable C, we're using to represent outcomes for the coin flip. And random variable capital D, we're using to represent outcomes of the die roll. And so for each entry, for example, in the first row, first column, that corresponds to the co-occurrence of instantiations for these variables, in particular, C equals heads and D equals 1. And so we calculated where we left off these probabilities for that random vector instantiation. We have 1/2 probability for the outcome heads. We have 1/6 probability for the outcome of 1. We multiply the two together and we get 1/12. And one of the observations we made is that we have 12 cells in this distribution. All of the outcomes are equiprobable, so it's a fair coin and a fair die. And if we add up that probability mass associated with each of the joint instantiations, we get 12 times 1/12, which is exactly 1. And so we'll learn later today that to be a proper probability, we have to have what's called the law of total probability satisfied, that the probability defined over all of the possible observable outcomes must add to 1. And that is the case whether it's a probability over a singular random variable or a random vector, namely a vector of random variables. Okay, any questions? Jar your memory? No? No questions? All right. And so with this joint probability, we talked about this idea of marginalization. And that was the mechanized process for how you calculate the probability of a single variable within this random vector. And we said with that, it's not enough to consider in isolation the instantiation for that or measurement or outcome for that single random variable. You have to include all of the other outcomes or instantiations that will appear for the other variables in your vector. And the reason for that has to do with that very fact that in order to be a proper probability, you must sum to 1, and that won't be the case if you don't account for all the instantiations in your random vector. And so here we said, for example, if you wanted the probability that your coin flip outcome or instantiation, C will equal H for heads, you take that column for heads, and for each possibility of C equals heads, you're going to have an outcome for the die roll of 1 through 6. So you have to add all of those entries together in order to calculate that probability for C equals heads. And so we can marginalize, in this case, down the columns. Likewise, we can do the same thing for the singular probability or so-called marginal probability associated with the outcomes of the die roll. And in that case, you marginalize across the rows. Okay. Any questions? Jar your memory? Yeah? All right. And I'll warm you up a little bit, figuratively. All right. So let's continue on with this idea, excuse me, of variable couplings. And so we're going to begin with a definition of something called covariance. And it is related to variance, and certainly covariance is precisely the variance when you're talking about a single variable. And we said back then that the variance is a measure of the dispersion, or more correctly, the magnitude of the dispersion of random variable relative to the center of mass or the center of the distribution. Now, when you have a random vector, what we're concerned about is the relationship between individual variables in that vector. What is this, what we're called coupling or linkage? And what I mean by that, I'll sort of ground that out in these two figures down below. I'll direct your attention to the figure on the left, your left, and we have on the horizontal axis economic growth, and on the vertical axis, we have stock market return. And so when we talk about economic growth, we refer to the output of all of the commercial businesses concerns within a country, county, state, in some locale. And so when you measure economic growth, the unit of measurement is percentage increase. Now, when an economy grows, it means that more goods and services are being produced. And as more goods and services are being produced, those companies become more profitable, and therefore their value goes up. Now, as their value goes up, because they are worth more than they used to be, their stock price also increases. And so, for example, if SoFi Technologies, a financial services company, if their business increased by 20%, their stock is also going to go up. Now, does the stock go up commensurate with the economic growth? No, absolutely not. What is the rule of thumb? Well, if you can figure that out, you should be in the finance industry, because there's no one-to-one correspondence for that. But what we see here for stock market return, that talks about dollars, and we can assume US dollars in this case, and each point corresponds to the amount of economic growth, let's say if that were 15%, and then the vertical axis corresponds to the return for that share price, right? The security. Any questions about that graph? And so higher means better, because the greater the stock market return, the more value or more valuable that particular investment instrument is. And so one of the things you'll notice, if we go from one measurement to the next, we notice that there's this relationship. If we were to draw an ellipse around this point cloud, I wish I were taller or had a little, kind of ruler or something, we notice that for some unit step increase in economic growth, going to the right on the horizontal axis, there's a commensurate unit step increase going up in terms of stock market return. And so one of the things that we enterprise to know when we're extracting insights by looking at the scatter plot for that particular graph is, what is that linkage? Because if that linkage is stable, is predictive, then we don't even have to look at stock market return. Effectively, we can look at the change in economic growth as a proxy for the amount of increase we're expecting to see in the stock market return. And so we need a measurement of that, and that measurement is precisely covariance, which we'll talk about, a type of probabilistic average. This particular graph, economic growth versus stock market return, you'll notice that this point cloud, this ellipse, it's sort of sloping upward, right? There's a positive linkage. If we increase in the positive direction in economic growth, we increase in stock market return also in the positive direction. It gets bigger, okay? I'll direct your attention to this graph on the right-hand side, your right. On the horizontal axis, we have world oil production, and the unit there is barrels of oil. I'm not sure why they say barrels and not liters. I don't know the history, but nonetheless, with world oil production, if you have an increase in the number of barrels, so you're going to the right on that horizontal axis, that means oil is more abundant. And we know at this juncture in the course that gasoline comes from oil, and supply and demand says the more of something you have, the cheaper the price gets, okay? So what we notice here is the converse of what we see in that first graph. If we have some unit step increase along the horizontal axis in oil production, we see a unit step decrease in gasoline price, where the unit for gasoline price is in dollars or whatever local currency they're talking about. And so in this case, our point cloud, we notice this ellipse is sloping downwards. So that means if that relationship between barrels of oil and the gas price in dollars, if that relationship is very, very strong, then just by seeing oil production go up some amount, you can count on or rely on or expect there to be a certain or particular decrease in gas prices. Does that make sense? Any questions? Now, this particular relationship is a so-called linear relationship. If we were to draw a best fit line, or a line that's sort of in the middle of the data, that line will be sloping upwards in the left-hand graph. That line will be sloping downwards on the right-hand graph. And there are all sorts of relationships. Linear is the easy one. There are lots of other measurements of coupling between variables that account for nonlinear relationships, things you can't describe as a straight line. Okay, any questions about this? Does that make sense? Yeah, all right. And so here up above, we have covariance. And like variance, this is a special type of dispersion, but this dispersion talks about this idea about the coupling as these data points, these variable measurements, are spread out around the center of their respective portions of the distribution. And so here we have a probabilistic average, or covariance, between two variables, x and y. And it's not limited to two variables, but we're just going to talk about the two variable case because we don't have linear algebra as a prerequisite for this class. So here we have the covariance between two random variables, x and y, is the expectation of what? The product between two things. Those two things are the difference between each random variable's outcome, x and y, and the center expectation of x and the expectation of y. Now, one of the things to notice here is that if this difference, x minus its expectation, is positive, and this difference, y minus its expectation, is also positive, then the covariance is going to be positive. If the two differences are both negative, the covariance will also be positive. But if the signs of those two differences are different, one's positive, one's negative, the other's positive, you're going to have a negative covariance. Now, if we had, instead of two variables, x and y, the covariance between x and x, that's exactly variance that we talked about. And so when we talk about covariance between variables, sometimes, and I'll direct your attention to the board here, they talk about, in the multivariate case, a covariance matrix. And each entry of the matrix corresponds to the covariance between two variables, a variable selected from the rows and a variable selected from the columns. So in this cell, we have the covariance between x and x. That's nothing more than the variance, sigma squared, of measurement x. In this cell, this is the covariance between y and y. That's just the variance of measurement y. Now, along the reverse diagonal here, you'll notice we have sigma yx and sigma xy. This is the covariance between variables x and y. Now, of course, I'm using sigma here. It's like, I thought you said sigma was standard deviation. Yes, it is for the single variable case. But when you're talking about multivariate distributions and you use this subscript, this refers to the covariance between those variables listed. Any questions about this? Does that make sense? Okay. And so this covariance, excuse me, is nothing more than a probabilistic average. We have x minus its mean, x minus mu sub x, and I use the subscript there on mu, so you know which mean it is. And we have y minus mu y, and we multiply that by the joint distribution, that same distribution that we talked about before. And so this joint probability talks about the probability of a particular instantiation of measurement x and measurement y, right, from some joint probability table listing. And then we multiply that as the scaling, the weight, with the product of the differences between each variable and its mean. Okay, any questions about this? Does that make sense? Yeah? Okay. And so this covariance, of course, has a little bit of a flaw. This is another mathematical oops moment, and there are many such oops moments in mathematics. You're comparing variables, things like barrels of oil and dollars, you're comparing the coupling between quantities that have kind of weird units. And so, like we talked about with variance, we might say temperature squared. It's kind of hard to understand what that variance means relative to temperature, the measurement type, because the units are weird, right? Temperature squared, degrees Fahrenheit squared. What does that mean? And so instead of saying our covariance, which is a valid measure, oftentimes we normalize this in a way akin to what we did with the variance. We need to get rid of the units. Because when we talk about coupling, we want to know, what is this degree of coupling? And covariance doesn't really tell you that naturally, so you can understand it in a way relative to the measurements, these variables, big X and big Y in this example. And so an example of that is if we look back or think back to the economic growth graph on the lower left-hand side, we said percentage increase is the unit for economic growth, and dollars is the unit for stock market return. So we have a unit called percentage increase dollars. What does that mean? If percentage increase dollars is high or low, what does that really mean? I don't know. It doesn't really make sense. Okay. And for the world oil production chart, we would have units of barrels for that first difference, X minus mu X, and we'd have dollars for that second difference, Y minus mu Y. So we have barrel dollars. Okay. What is the linkage between these two measurements? It's 25 barrel dollars. What? I don't know what that means. Okay. And so how this is remedied is by taking our covariance, and we need to express it as a proportion. And we also need to clean up the units to something that kind of makes more sense internally. And so what we are really asking, or what's really helpful, is to express this variable linkage in an idea of the proportion of that dispersion, the spread of the measurements due to the coupling or contributed to this linkage between those measurement types. And so that's called correlation. And what correlation does, Greek letter rho, it takes our covariance, our linkage between X and Y, and it divides by the standard deviation of the first measurement X and this for the standard deviation of the first measurement Y. And in essence, what that does is cancels out the units, but it also expresses it as a type of proportion, almost like a percentage, but it's not a percentage. I'll stress that. Any questions about this? Does that make sense? Now, when you talk about correlation, especially in the Python APIs, you'll see an API call for something like correlation coefficient, right? And when you take the correlation or compute the correlation coefficient between two variables X and Y, you're going to get the correlation coefficient matrix. Now, I'm calling the correlation coefficient matrix rho here, and you can label the rows X and Y, are two random variables, label the columns X and Y. So this entry is the correlation between measurement X and itself. This entry is the correlation between measurement Y and itself. Now, how does X vary with X? 100%. How does Y vary with Y? 100%. And so you're not concerned with this coefficient matrix or correlation with the diagonal. You're concerned with what's the off diagonal. And so this entry is a correlation between measurement Y and X, and this measurement is a correlation between measurement X and Y. Now, of course, these two entries off diagonal are going to be the same. Why are they the same? Well, don't believe me, let's look back to the definition. And so here, if we have the first term, X, second term, Y, if we reverse the parameters to covariance, we would have Y minus mu Y as the first term, X minus mu X as the second term. So multiplication is commutative. It doesn't matter if we multiply the first term by the second term, but we have the second term followed by the first term. And for that reason, correlation is also commutative. Therefore, these off-diagonal entries, correlation Y with X, correlation X with Y, are exactly the same. Okay, any questions about this? Does that make sense? Okay, so all correlation is the expression of covariance scaled down almost like a weird kind of percentage. And so when we look at correlation, correlation has an outcome that's between -1 and +1 on the real number line. Now, I draw the square brackets. If you're not in computer science, this means a closed interval. If we have the number line, closed interval means here's 0, here's -1, here's +1. It means we're including in that set of real numbers the endpoints, -1 and +1. And so here, our correlation, the range of this function is between +1 and -1, where the strongest correlation is a 1, whether that's positive or negative. And a positive correlation looks like this graph on the left, your left. We have a unit step increase in one measurement is exactly the same unit step increase in the other measurement. That's what a perfect correlation looks like in the positive direction. Perfect correlation in the negative direction means a unit step increase in one variable, one measurement, is commensurate with unit step increase in the data of a unit step decrease in the for the other measurement, and it's the same amount. And so if we do our best fit line to these point clouds, we're going to get a 45-degree slope increasing for +1 correlation, and we're going to have a 45-degree slope in the negative direction for a -1 correlation. If you have a correlation of 0, that means there's no linear dependence or linkage between the two variables, and everything between 0 and the extremes, be they +1 and -1, is scaled appropriately. Any questions? Does that make sense? Okay. And so later in the semester, we'll talk about other stuff like entropy and mutual information and all sorts of stuff that are amenable to nonlinear relationships. And the reason why I stress linear is that this is just a tool. Not every tool is appropriate for every single scenario. And part of what I hope to build in you in this semester, in this class, is an eye towards which choices you have and why you'd make particular choices when you're enterprising to extract insights from your data. Any questions? Yes. Are the values? Those are the values. That's the range. Those are the set of outcomes that the correlation function gives you. But the correlation coefficients, it's this matrix. It's the correlations pairwise between two measurements, where you have the measurement with itself, and the different measurements, what that linkage is. And so each one of these, row X, X, row X, Y, row X, Y, and row Y, X, all of these are going to be in that range between -1, +1 on the real number line. So each one of these entries here, you're going to have +1, +1. You're going to have some value between 0 and, some 0 between -1, +1, and you can have the same value here that you have up there. Okay. Any other questions? Does that make sense? And so the value is always in this range, but the coefficient matrix is just showing you all the different correlations between two variables. Okay, and you can do it in more than two variables for correlation coefficients. You could have a random vector of like 100. It'll give you a correlation matrix for that. Okay, any other questions? No? All right, make sense? All right, so let's finish up that module. Let me switch the slide deck, and every time I exit PowerPoint, it sort of kills this, the screen share. So I'm just gonna exit. And this was what, 5? So let me get rid of that. That's 6. Let me start the new share. That's 6, share. Let me go to slideshow. And then you're not seeing what's on my screen. It's like in this weird presenter mode. So let me go slideshow there, and hopefully it'll show up well on the recording, because it doesn't show you what you're going to see in the recording until you're there. Okay. So let's hide the meeting controls. On the clicker. Oops. All right. So let's jump right into more formal definitions of probabilities. We just got done talking about correlation and covariance rather, and correlation. And so We talked about random variables, and we talked about this idea of um, measurements over raw events. But we didn't really talk much about what a probability is really defined as mathematically. And I wanted to give a little bit of rigor because it's important, and also cover some background material, duly purposed to get you comfortable with some of the notation that we'll look at, because the prerequisite for this class is CS120 and calculus. I don't assume that you've had other computer science stuff because our distribution is also from first year to grad student in this class across various majors. And so suppose we have our sample space. As we've talked about it, omega, we said, represents all of the possible measurable outcomes you can have from some experiment or trial. But we need, in order to talk about things in the real world over which we might wager, for example, we need to be able to combine events to build so-called complex events. And so we're going to cover some machinery that allows us to talk about that. And we're going to use that to talk about the definition more formally about what a probability is. Okay. So suppose we had an example and you had a game of chance and you saw the statement, she rolled an even number on the die, right? How are we going to talk about that? No, we know that even means the 2 outcome or the 4 outcome or the 6 outcome. But how do we get there from just this idea of I rolled a 1 or 2 or 3? And so we have, my clicker just froze. What does it mean to be an even number on the die? We need a way to combine these singleton or individual outcomes that we can measure into so-called complex events, because that's what our discourse is over. And so this idea of a probability is nothing more than a function. And this function says if you give me some member of this collection M, script M, a set, we'll call that our sigma algebra, and I'll fill in the details of what that means. It associates it with a value on the closed interval on the real number line. Thank you for the door. On the real number line between 0 and 1. And so what is a function? A function is nothing more than a mechanism that relates two things, elements of one set to elements of another set. And so way back when you learned, I guess it was arithmetic, you had something, I don't know if they still do it this way. I wasn't in grammar school for a long time. You have some f of x, x squared, and you said you're going to input some value like 2, and you're going to get some other value out, in this case, 4. Now, your algorithm is the procedure for, in this case, repeated addition, right? All right. Which is multiplication. You multiply something by itself some number of times. And so this function is formally a collection of all of the values you can input from that set on the input side with all of the values that you can get as a result of this mechanized process. And so probability is nothing more than a type of function. It's an association between elements in one set, the set on the left, our domain, and values in that other set, the set on the right, collectively called the range. Now, to be a function is not just an arbitrary association. You have to have certain properties called one-to-one and onto. And that means that all the values in the domain are associated with some unique value in the range. And then onto means that for every value in the range, if you were to go to the left, that's going to be unique. Now, probability is not what's called one-to-one and onto. It's called a many-to-one function. And the reason for that first statement, one-to-one and onto, is because you can invert things, right? To be able to say, if I undo that function, do I get back to the original thing in the domain that I started with, that set on the left? But nonetheless, a probability is formally defined as a function that associates with each element of M, what we call a sigma algebra, some number between 0 and 1 inclusive on the real number line. Now, we talked about when can I see you again and per centum, that all still applies. But it's this idea of what this script M is that gives us the machinery to be able to traffic in so-called complex events, like she rolled an even. Okay. Any questions? Does that make sense? And so what is this script M? Sometimes in some textbooks, they note a sigma algebra using capital sigma, and they give it a parameter of the sample space. I'm using M and not sigma, and I just show you that notation because depending on what you read and which math tradition someone came from, they might use that other notation. And so the question then is you have a collection of objects, and that is what probabilities are defined over. And this particular collection, a sigma algebra, represents combinations of objects that you can carve out from your sample space omega. And so when we see the phrase she rolled an even, well, even is either the 2, the 4, or the 6. And how we represent that formally is having a set, which is a collection, and that set contains 3 objects, the 2 object, the 4 object, and the 6 object. Any questions about this? Yes. Yes. All of the possible things over which you could define a probability. Because in order to define the function, you have to list out the things for which you can have a probability like associated. Yes, absolutely. Any other questions? Now, just because you define a sigma algebra, it doesn't mean that everything possible in this sigma algebra will have a probability. It depends on the system that you're dealing with. But in order to have a probability, the things over which you associate a probability or with which you associate a probability have to be in the sigma algebra. Okay, so the next question then, what kind of collections from our sample space omega? How many are there? How big can the set of collections get? That's a really important thing to consider. So let's begin with our framework of sets, and we're going to use a Venn diagram, which is just a visual depiction of collections of things. And we begin with what's called the universe. The universe is a set of everything you could possibly consider, like the universe around us, right? So with this Venn diagram, it's graphical, and we have our universe here labeled as omega, our sample space. In this particular case, this is omega die. It's all of the possible observables you can have for the outcome of a die. We have object 1, 2, 3, 4, 5, and 6. Okay. Now, with this Venn diagram, every time we talk about something we can observe, an event, we're going to carve out from our universe some collection of objects. Now, to be a set mathematically, there's a rigorous definition. You can have at most one of every object represented. So you can't have the set 2, 2, 4. It's just 2 and 4. Does that make sense? Any questions? No? All right. And so we have our events that we draw from it. And so here in the yellow or gold, or my crayon box growing up only had 8 crayons, so I always struggle with colors. I don't know if that's goldenrod, gold, yellow. It looks yellow to me. All right. So we have a yellow circle here. And in that yellow circle, we've carved out from our universe the 2 object, the 4 object, and the 6 object. So we built that collection. Now we give it a name. We call it the set of evens, but you can depict it with our Venn diagram by just drawing an envelope that collects together some subset of objects from the universe. Now, if we represent it mathematically, we would give it a name, and I use that subscript even because it looks nice on the screen, and that consists of 2, 4, and 6. And so when we talk about this event that we can observe called the events, it's really just a collection from our sample space, our universe of consideration, our sample space omega, but we give it a label, and mathematically we can write it out using our set notation. Okay, any questions about this? Does that make sense? And so here's another one. Here's another set, and this set contains the 5 object, and the sixth object. We've carved this out of our so-called universe of consideration, sample space omega, and we can give it a name. We could call it the event 5, 6, or we could give it a more descriptive name, greater than 4. So you could now construct a special type of observation, a complex one, where you could say, what is the likelihood, the probability that someone rolls the die and it's greater than 4? And so we really need this framework of being able to carve out collections of objects from our sample space, our universe of consideration, in order to traffic in arbitrary things over which we can define probabilities or associate probabilities. That makes sense? Any questions? All right. And so here's another one, okay? 1, 2, 3, and 4. You could call it the event of rolling less than 5. Now, there's no formal way about how you name these things. There are names like evens and odds and less than this and greater than that. It doesn't really matter what you call them, right? But the main takeaway here is that now we can associate or name as events things that just aren't singular observations. We can have collections, arbitrary collections. Any questions? Does that make sense? All right. And so another important thing that we consider is, let's take a look at this event. Now you notice here in the yellow, we have everything without 5 and 6. So we've circled 5 and 6, and that's in the blue. And the yellow, things that we're selecting, is everything that is excluding 5 and 6. And so for that, we call that the complement, not. And so we have event 5 and 6, and we draw this vertical bar over it to say everything else in the universe, not including this stuff. And so this idea of complement is really, really important, and we'll allude to that later. We could note this in set notation here in the Venn diagram, or we'd say event 5, 6, but we complement that, right? Vertical bar. All right. Any questions? Does that make sense? And so if we have an arbitrary event, in this case A, we draw it, we label it, we talk about it, and that event carves out from our universe of consideration some subset. That subset could be everything, that subset could be nothing, or that subset could be something in between everything and nothing. Okay. Any questions? Does that make sense? No? All right. And so this idea of a sigma algebra, and I also want to hopefully get you comfortable with reading some of this notation. It's a little bit to unpack. In this particular book, I can put an excerpt on the course Canvas site, but it talks about what it means to be a sigma algebra. Because without the sigma algebra, you don't have things over which you can define probabilities. And so here you can think of it as a 3-step litmus test. And if some function, or rather some set, I should say, satisfies these 3 tests, then you say, yep, that's a sigma algebra, and I can start to talk about probabilities associated with each element of this collection. And so the first one, it says that to be a sigma algebra, you're proposing that this set called script M, you're proposing, hey, I think this is a sigma algebra. Okay, prove it to me. Prove step A, prove step B, and show me step C also holds true. So to be a sigma algebra, step A says it has to include the sample space omega. So that means our sigma algebra is nothing more than the set of collections that you can make by carving out different subsets of our universe. So it says, okay, well, omega has to be one of them. So here we have our sigma algebra. One of the requirements is that the collection must include the entire sample space. So what is this entire sample space? What does that mean? It says, if I roll the die, something's going to happen. That might seem nonsensical, but this idea of something happening assured, that's associated with probability 1. But you have to have that in existence as something over which you define a probability. So this anything event has to be present in your sigma algebra, and because that allows you to define what probabilities are. Okay. Any questions? Does that make sense? Okay. And so if we consider everything in the universe, that anything event, well, that's here. It's all in yellow. We've selected that subset, which is every possible observation as a singular observation that we can have from sample space omega. Does that make sense? Any questions? Now, the next criterion for this idea of, yep, you're an honest to goodness sigma algebra is this idea. Well, if you have an event contained in your sigma algebra, its complement has to be contained. And the reason why the complement has to be included is if I said she rolled an even on the die, you have to be able to say she did not roll an even, which are the set of odd numbers. And so the second litmus test, honest to goodness, you are a sigma algebra, you have to satisfy this. If a particular collection carved out of sample space omega is in script M, its complement also must be included. Does that make sense? All right. And so here, all right, if we start with the anything event, which is a requirement, litmus test A, well, what is the complement of anything? Let me ask you, what's your intuition? Nothing. The complement of anything is nothing. Okay. That means you roll the die, you don't see anything. Nothing happens. Now, it seems kind of weird, but you need this idea of the complement of your collection included because it makes more sense when you say an even or not an even, right? The odds. All right. Are there any questions? Does that make sense? All right. No? Doesn't make no? Yes, no? But not at 9 in the morning, right? Okay. So if we are given the anything event as a requirement, we have to have the nothing event, which is the empty set. And we note that as this 0 with a slash through it, like Ghostbusters, you know. At least I see Ghostbusters. It sounded funny when I made the slide. All right. So the empty set is the complement of the everything set. Okay. So how in the world do we get to probabilities? Well, this is the empty set. You'll notice here in the Venn diagram, we have sample space omega, our so-called universe of consideration, and it's all in the blue, or I don't know, is that magenta? Or I don't know the 64 crayon box color. I just know the 8. That's blue, light blue. Right? Anyways, so it's all light blue. So that means we're not carving anything out. It's a subset of nothing. And so the empty set, you just have your set notation, and there's no object in the empty set, no outcome selected. Okay. And so now we have our anything event. In the case of the die roll, 1 through 6, we have the nothing event, the empty set. And now this is where the business end of probability is. We have some event, which is not the anything event and not the nothing event. Okay. But this idea of that second point says if you have some event in there, its complement must be there. So the reason for empty set is because we have the anything event. Does that make sense? All right. Any questions? No? All right. So here, if our set included what we're naming even, which is the collection 2, 4, and 6, we'd have to have not even, which is the collection of 1, 3, and 5. Now, of course, 1, 3, and 5, we give that a name. We call them the odds. Okay? All right. Because for any sort of probability, you can, in your discourse, talk about an event, but you should also be able to talk about that event not occurring. Does that make sense? Any questions? No? All right. And so what is not even? Well, in the Venn diagram, we take even, that's our universe, what's left, and we carve out of that everything that's outside of the evens, and that's in the yellow, which is 1, 3, 5, the odds. Okay. Any questions? No? And so this last one, sometimes it's called sigma additivity. And what it says is that if you have some event that's in your sigma algebra, so too are the combinations or the union of those events. And I'll explain what I mean by that. So the key words here is finite and countable. So every finite or countable collection is contained along with its union. So if you have an event called 1, an event called 2, those basic or those singleton observations we talked about, that is more understandable in terms of the outcomes of a die roll, then all possible combinations of those things are also in your sigma algebra. So let's look at this more casually. This idea of a complex event is nothing more than the union or putting together of more simple events. And so if we take our sigma algebra, right, and let's say we have two events, E5, the 5 outcome, E6, the 6 outcome. If those two, E5 and E6, are in the sigma algebra, then the union of the two, E5, 6, must be in the sigma algebra. Does that make sense? And so it's closed under union, okay? Meaning that if you perform the operation, the result of that operation is also in the set question. Okay.
Saying that the union of any observation
should be included as well. If the individual event is there, you have to see the union of all possible groupings of those events. Okay. Any other questions? Yes. Yes, because you can't have combination of 5 or 6 without having had 5 individual and 6 individual. And so, and that also means, and I'll get to that. I don't want to jump ahead. So to answer your question, yes. Yes, yeah, your question. That's the minimal. So there are boundary value conditions that tell you how small it can be and how big it can be. And just because you can form a probability over something, it doesn't mean that it's included in that particular one. You have a sigma algebra, and that sigma algebra tells you over what you can define probabilities, but it doesn't tell you how big it should be. It says what's the biggest it could be and what's the smallest it can be. And that's just a corollary, or what follows from those 3 things in the litmus test. Okay. Any other questions? No? All right. And so if you have these simple events, E5 and E6, in the sigma algebra, to be valid, you have to have the union of those two. All right. And so let's take a look at this sigma additivity in action. So you have all sorts of collections from your sample space omega, your universe of consideration. And we said you have to have the something event and the nothing event, okay? We said if you have these observations, like what we were calling the singleton outcomes, when we roll the die, you can observe a 1, 2, 3, 4, 5, or 6. Sigma additivity, that third litmus test, says you have to have all of the ways of doing a union among those. So let's take a look at this. And so if we were going to do a union, we would have the union between pairs. And I call that the two-way events. And so if we have the two-way events, that's 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6, 2 and 3, 2 and 4, the so-called two-way events. You take unions of all possible pairs that are not equal to one another. Does that make sense? And so that's, if you have singleton events, you have to have the two-way events, okay, complex events. And if you have the two-way complex events, you can take each one of these two ways and take the union with a singleton and make a three-way event, okay? So with the three-way collections, now you have three-way collections. You take a three-way collection and you take the union of that with a one-way collection. That's now a four-way. And then you do it as a five-way collection, right? And so you build up all these different collections of different sizes. And that's just a consequence of that third point, that third litmus test C, our so-called sigma additivity. Does that make sense? All right, so it just happens that there's a three-way collection, 2, 4, 6, that we just happen to name the evens. There's a three-way collection called 1 through 5, which happens to be the complement of 2, 4, 6, but we call that three-way collection the set of odds. This collection 2, 3, 4, 5, 6, we could call that the complement of the 1. What's the probability of not rolling the 1? Does that make sense? Are there any questions about this? All right. So from this, to your question, there is no requirement about the size of your sigma algebra. And so whenever you define a system, you often define what are called the boundary value conditions, right? What are the extremes, both on the big side and on the smallest side? Because we said for that third part, that point C, said if an event is in your sigma algebra, all the unions of events. So the question then is, what is the smallest a sigma algebra could be? And what is the largest a sigma algebra could be? So on the smallest side, you said you're required to have the anything event. What's the probability that I get a side of a die, right? Okay. That is this one that has the sigma algebra, omega, something happens, and its complement, which is a requirement. Now, in this case, there are no other events, so we don't have to build them up by union. Now, the other one is the so-called dense sigma algebra, as it's sometimes called in the literature. That's the biggest a sigma algebra can get. That's what I just listed on the previous slide. You have the anything event, the nothing event, the singletons, the two-way, the three-way, the four-way, and the five-way. That's the biggest that your sigma algebra can be. Now, this biggest sigma algebra, the so-called dense sigma algebra, is the richest, most descriptive sigma algebra because it talks about anything that you could ever talk about in terms of subsets carved out of your sample space omega, your universe of consideration. Okay. Any questions? Does that make sense? Yes, question. Yes. And if that were what you cared about, then your sigma algebra would have the anything event, the nothing event, the one event, and the not one. But if you have the one and the not one, that's sufficient because you have no other events. You just have to make sure that you're satisfying that additivity, which is that point C. Okay. Any other questions? No? Make sense? Okay. So what is this dense sigma algebra? It's a so-called power set. The power set is the selection of all possible subsets. And the size of this power set is 2 raised to the cardinality of the size of the sample space. And where that comes from is if we list out our sample space, if you're building the power set, each element can either be in as a collection or out as a collection. And so, for example, if we were to talk about the odds, 1 is in it, 3 is in it, 5 is in it, but 2, 4, and 6 are not. And so if you're ever trying to build the dense sigma algebra, you have to have all possible combinations. And if you're going to count the number of all possible combinations, you have to have 2 to the cardinality of the size of the sample space. Okay. Any questions? Now, just because a sigma algebra can be dense, it doesn't mean that you have to use it, right? You only use, to your question, you only use what you need for the system of discourse. Okay, any other questions? No? All right. Okay, and so this idea of complex events, a probability is nothing more than a function that associates with elements of the sigma algebra a number on the real number line between 0 and 1, our proportion. All right. And so here, if you wondered, why does equiprobable mean 1 over the cardinality of the sample space? Well, I didn't want to tell you that, but the reason has to do with if you have n possible outcomes, and I'm going to use lowercase omega to represent each singleton event in our universal consideration. And so if we add them all up, we know the probability of something happening is 1. Something always happens, right? If you have the event of, in the die roll, 1, 2, 3, 4, 5, 6. Okay. Well, if we know the probability of omega is 1, and each one of the individual events, there are n many of them, are the same, if we add them up here, we're adding up n many of something that's the same and is equal to 1. Well, if you solve for n, it's just 1 upon n for each thing. So that's precisely where it comes from. So if you're given this idea of a fair system, a fair die, a fair coin, you can assume that all of the objects under consideration in our universe of consideration they have equal probability. And knowing that each one is 1 upon n for n many outcomes, we can use that to construct our complex events. And so here, first, any questions about this? That makes sense? All right. So here, when we talk about sigma additivity, we're constructing a complex event from each one of these singleton objects from sample space omega. So we can build an arbitrary event E as the union or the combination of a set of these simple events. We can always decompose it. And if we know each one of these lowercase omegas, you have T many of them, as a union to construct our complex event E, we're just going to add up the individual probabilities. And so the probability of your complex event is just the sum of the individual probabilities of the simple events, the singleton events. We know each one is 1 upon n. And so that means, in this case, if we have T of them, we add 1 upon n with itself, T many times, and we get T over n as our probability. Now, sometimes you'll see things like a probability of a complex event is the counting of the so-called favorable outcomes divided by the possible outcomes. And so essentially what we're doing there is we're taking the number of singleton events that are in union to form this complex event. That's the number of outcomes in event E, and we're dividing that by the number of outcomes in sample space omega. And so if we said, what's the probability of rolling an even? Well, the set even is the union of the 1 with, of the 2 with the 4 with the 6. We say 1 upon 6 plus 1 upon 6 plus 1 upon 6, that's 3/6, or 50%. Said differently, if we know the event 2, 4, 6 has 3 things, we count how many things are in it. 1, 2, 3, 3 things. And we divide by the sample space cardinality, which is 6. And so when you see probability of some complex event is the number of favorable outcomes divided by the possible outcomes, we're really, as a sort of heuristic, a quick heuristic, we're counting all of those simple events in union for that complex event. Does that make sense? Any questions about this? No? All right. And so I promise you, this is the most theoretical it's going to get. We're going to have to talk about conditionals. And so when we roll a die and we want to know what's the probability of getting an odd number of dots, well, we have sample space omega die. We have our dense sigma algebra if we were to use it. We know here's our dense sigma algebra. We list out the singletons, the 2 ways, the 3 ways. We have our sample space omega, the anything event, and we have the nothing event. We know the probability of odd is the probability of the odd event. It's a complex event, which is a 3-way union. That's the probability of 1, 3, 5. Okay. We could either compute it separately or we just count how many objects. We have first object, second object, third object. So that count is 3, the favorables. And then the total is 6 because the cardinality of omega die is 6. So we divide 3 by 6 and we get our 50%. Any questions about this? And so when our event gets more complex and there's other complexity, I'm going to peel back in subsequent modules, you count what you're looking for and you divide by the cardinality of the sample space. Any questions? No questions? I had budgeted for more questions, so we can always end a little earlier. All right, so with that, I'm going to end there. And hopefully this has given you a little bit more visceral understanding about where this comes from. And we're going to use this idea of favorable over total going forward when we calculate these events, because it gets more complex, so much so that you can't just kind of enumerate like we did with the coin flip or the die roll. Okay. Any other questions? No? I look forward to your submissions. Please submit early if you have it done and do your happy dance. So I'll see you all on Wednesday.